All right, so this video is going to be on dihydroxylation, which is basically adding two alcohols or OHs to an alkene. So there's a couple different ways to do this, and one way we already know, right? And so let me just introduce that or remind you of that. So we know that once you add MCPBA, right, we get an epoxide. Okay. All right, here we go. We got an epoxide. Remember, the MCPBA can approach from the top or the bottom to give you the wedge or the dash for that epoxide. And this is by definition Syn Addition, right? And so we get the oxygen attached to basically the top plane or the bottom plane of that double bond. And we have two epoxides. Now, what do these epoxides do? That is the question. All right, so let's take a look at reactions with epoxides. So again, we already did this, right? So what am I getting at? Well, we're going after a specific reaction. So we have this epoxide with the methyl there. Then we throw in a nucleophile. Wait, let's keep that methyl there. And if we have a good nucleophile, where does the nucleophile attack, right? Well, it attacks the least substituted carbon, okay, resulting in a substitution reaction. Remember, this is like an SN2 reaction. So we get inversion as well as a new product, a new substitution product. There was the other direction that we could head with these reactions, and that was adding acid and then a weaker nucleophile. So when we have the acid with the weak nucleophile, what did we attack? Well, we attacked the more substituted carbon. Okay. Pretty much these reactions were really similar, but what they resulted in, or potentially resulted in, was the formation of two alcohols, right? Now let's see. So, boom. Let's draw an OH there as well as an OH there. We could also have the wedge and the dash switched. Okay, so let's see. We'll just keep that as in that direction. So we'll give it the methyl, the wedge going up, and then we'll swap those OHs. Okay, so what were the reagents required to make that happen? Because this is the ideal product for the subject of this video, right? Dihydroxylation. We form two OHs on there. So look at the OHs. These OHs are, in fact, the source of that nucleophile, right? Now, if we come back here, take a look at that nucleophile. What's a strong nucleophile with an OH? Well, it's a hydroxide, okay? So we can do 1 hydroxide, 2 water, just to get that alkoxide protonated once the ring pops open. Again, we know this reaction, but let's see, boom, pop that open. We've got, it's an SN2 reaction, right? So it's backside attack, which means that OH is going to have a dash, and then the alkoxide pops open, gets protonated by water, giving us that diol or 2 alcohol product. Okay, let me just move this over real quick. Okay, let's try again. Oh my gosh, I do not like my iPad or my computer or technology. All right, okay, let's try again. All right, see that? I'm getting mad. Be aggressive. Be aggressive. Here we go. All right, I think we figured it out, folks. Oh my gosh, this is me right now. Haha. Haha. Current mood. Oh my goodness. Okay. Anyway, let's get back to chemistry, y'all. So once we protonate that alkoxide from the water, we will get this guy right here. A sigh. Look, we made it. We finally made it to the final product. Yay. Okay. Anyway, that's a diol. See, DIOL. That's 2 alcohols on that epoxide. Or I'm sorry, on that were added to that alkene from the epoxide. And remember, of course, that the epoxide can also be from the other side. from the lower plane, and then that will give us a different diol, so a different enantiomer. Okay, and we should know the stereochemistry associated with these two guys or the relationship. So if you were to flip that guy, then you got your enantiomers, right? And so you should be able to do that. Remember, this is an anti-addition of those OH groups, and that's because they do not have the same three-dimensional orientation. So they're not in the same plane. One is wedge, one is dash. By definition, anti-addition. And that, let's see, when we throw in the sulfuric acid with water, we always protonate first. And then that allows us to attack with the weak nucleophile at the more substituted position. Again, it's like a pseudo SN2 because we still get inversion, even though it's at that tertiary carbon. We're getting an SN2 type reaction. Okay, it's kind of like a SN1 SN2 hybrid thing, but we get that inversion so that methyl pops up. We get the diol again. Look at the products. Okay, so I drew it weird, but that product is that product, and the red checks are the red checks. Like, those are the same exact products. I just kind of oriented the wedges and dashes a little bit differently, and that's these products right here. Okay, so it's important. Remember, anti-addition is from the epoxides. Okay, and so we can do it in a number of ways. We can do either with, let's write it here, so we got it in a nice organized fashion, but we can do it with the addition of MCPBA first, followed by water with acid or hydroxide. So it depends, acid or basic conditions, and it really just depends on the rest of the molecule. If the rest of the molecule is pretty sturdy or robust, you can have any condition, but maybe the rest of it will break down in under acidic media, and then you're going to need to choose the basic, or vice versa. So that's why you always want more than one option. Okay, but now what if we wanted the Syn addition to form our 1,2 diol? Okay, so meaning that the alcohols have the same three-dimensional orientation, and that is wedges or dashes. Okay, Syn addition. What reagents do we need in order to achieve this? Well, let's see. We got options, of course. We got to have more than one tool in our toolbox. So dihydroxylation, or Syn dihydroxylation, can be done using a couple different reagents. Okay, so I'll lay them out for you first, and then we'll kind of take a look at the mechanism. So KMNO4 with water and hydroxide. You've seen this before. This is potassium permanganate. This was, you probably saw it in like general chemistry, but we can also use osmium tetroxide with sodium bisulfite and water. Okay, they do the same thing, but they have their advantages or disadvantages. So it just kind of depends what you're trying to achieve in the lab or your resources. Okay, so let's take a look at the mechanism with potassium permanganate, water, and hydroxide. I'm going to do that mechanism only, but it's pretty much the same mechanism for the osmium tetroxide. Okay, they're metals with 4 oxygens bound to it, right? And they both achieve Syn addition to form this 1,2 cis diol. Okay, so a dihydroxylation with the Syn addition of those OHs. Okay, and of course they can be added to the top or the bottom. Just depends on the approach of the metal oxide. So the manganate or permanganate or the osmium tetroxide. So they both have this metal center with 4 oxygens doubly bound to it. Okay, and so, sorry, that's not doubly bound. That is negative, so it's got 1 bond. And this potassium permanganate basically approaches with the 2 oxygens on either side of that double bond, where the carbons are, and then you have an attack as well as the oxygen getting attacked. Okay, kind of like the other, we've seen that reaction, that kind of thing before when we formed the bromonium or things like that. So follow the electrons the double bond on one of the oxygens goes to the manganese, and that makes essentially we got two wedges on the oxygens because it must be on the top or the bottom plane, because you can't kind of go across on the top plane down to the bottom plane. The bond angles wouldn't work and the proximity wouldn't work either. So that's why this achieves Syn addition, because it's coming from the same metal oxide. So this is the manganese intermediate compound where we would then just add water to, and that kind of just breaks everything apart and gives you your diol. And just to throw some more vocabulary at you, just so you remember, this is a syn vicinal diol, right? So remember, vicinal means that those OHs are on neighboring carbons. And yeah, we achieved our desired final product. This mechanism more or less is the same with the osmium tetroxide. Okay, so just substitute OSO4 with the manganese. Okay, and then at this water step, we have the sodium bisulfite with water, and then you still achieve that syn vicinal diol. Okay, so this is also going to be called a cis 1,2 diol. Okay, lots of different ways to communicate this, and we should be aware of all of them. Okay. Okay, so why again do we have both options when they seem to be? I mean, the potassium permanganate works really well. It does need to be in basic conditions, otherwise it'll continue to oxidize your products. Osmium is actually better; it's more selective, but it's expensive and it's toxic. Okay, so we don't like toxicity, right? The toxicity of our chemistry. No! Alright, there you go. Sorry. I had to. You know how I roll. Music is running through my brainsicles all the time. We got this osmium 8 plus. That's the structure of the osmium. I told you it's really similar to the manganese. And then we get our cis diol forming. And during that process, we reduce our osmium as we oxidize the alkene. And so we go from an osmium 8 plus to an osmium 6 plus, which is, depending on what you're looking at, your sources, it could be either one of these guys right here. Okay, so those structures, or one could lead to the other, either way. But you take your osmium 6, right, and then you add N-methylmorpholin N-oxide. Sorry, I want you to make sure you can see the spelling for that. And methylmorpholin N-oxide. So the N's mean that's referring directly to the nitrogen in the compound, and you can abbreviate this as NMO. So if you put that on your reaction arrow, you just put NMO. And what happens is it oxidizes your osmium 6 plus to an osmium 8 plus, which is the reactive compound that does the oxidation of the alkene product or starting material to the alcohols. Okay, so NMO allows for the addition of osmium in catalytic amounts, and this will allow you to save money and the planet. Okay, so that means, like, let's say you had 1 mole of alkene. You no longer need 1 mole of osmium. You can add 0.01 moles, for example, and then you can add 1 mole of N-oxide or N-methylmorpholin N-oxide or NMO, and then that will oxidize any of your osmium to kind of create that catalytic cycle. That way you can use very little osmium to get the same product in the end. Now, granted, you do have an organic compound byproduct, but it's not nearly as expensive or as toxic as your osmium. And so there you go. And so one last thing I would say is that you're adding the NMO in stoichiometric amounts, whereas you're adding the osmium in catalytic amounts. And by stoichiometric amounts, I mean for 1 mole of alkene, you want 1 mole of NMO. Okay, because once you create 1 diol, you need 1 of the NMOs to convert the osmium 6 back to the osmium 8 to repeat that cycle. So there you have it. That's all, folks. Have fun.